Hello everyone, we are discussing model checking, specifically LTL model checking. In the previous class, we have introduced the syntax and semantics of LTL, right? So in today's class, we will take various examples and we will see how we can encode them in LTL language, okay? Just to recap what was in LTL, so we have 4 temporal property, A, which determines finally or in future, X is in the next state, something is going to happen. Globally means in all states, always something is happening, and until is something holds until something else holds, right? P until Q and so on. So there are 4 temporal operators, and we also have the propositional operators like not, and, or, and implication. And we have also shown what is the correct syntax and semantics in the last class, right? So we will follow correct semantics only. So now I will take various English statement which basically dictate some of the features in a system, and we will see how we can encode them in LTL. Okay. So the first one is the certain process is enabled infinitely often in a computation path. So here one thing is infinitely often, right? So I would suggest you note two things. One is enabled. So let's take the first example. The certain process is enabled infinitely often in a computation path. So there are two parts I would ask you to note. One is enable, which is the proposition, right? So basically the property I am going to write is in terms of the atomic proposition enabled, okay? But the other part is infinitely often, right? So I have to effectively model this infinitely often in LTL, right? So for a given statement, the first task is identify what are the propositions, and here the proposition is enabled, and I have to encode infinitely often. So what does it mean? Infinitely often means the enable is going to happen infinitely often, means if you are in some state, you will get some future where enable will happen. So think about this, F is the future or finally enabled, right? So it means if you just write this, then in future somewhere enable will occur, right? But I am saying this is going to happen infinitely often. So no matter where are you will get another future state where enable will happen. So this should happen globally, right? So that's it. If I try to encode this sentence, it is GF enable, right? Globally in future enable is going to happen, right? So that is infinitely often, okay? So this is what we have encoded. The next statement. So whatever happens, a process will eventually be permanently deadlock state. Again, you have to identify the proposition first, which is deadlock, right? And then what I am saying, eventually permanently, right? What does it mean? It means after some time, eventually means in future, right? This deadlock will become global event, right? So always permanently means it become a global event, right? So it will become permanently deadlock, right? So it is basically globally deadlock is going to happen, but it is happen in some future, right? So it is FG. So earlier was GF, which is infinitely often, and this is permanently. FG means permanently, eventually permanently, right? So this effectively means in future I will basically reach a state where after from state in always in all state after that deadlock will be true, right? So this is FG deadlock, okay. Now next is the third one. So again the statement says if any state, for any state, if a request occurs, then it will eventually be acknowledged, right? So I have basically two proposition, some request come and some acknowledge going to happen, right? So you basically request for something and then you get an acknowledgement signal, yes, I have received your request, right? So I have two propositions here, request and acknowledge. And what is saying that if request occur, say somewhere request happen, so I'm just request, then eventually means in future, right? Implies in future acknowledgement happen, right? And this is globally true because in for any state. So for any state is basically globally request happen request occurs implies in future, eventually means in future, acknowledgement is going to happen, right. So, this is G, request implies F, acknowledgement, right. This is what is this. This is how the encoding will happen for this statement 3. Okay. Let us take the fourth one. This is more or less easier now given the other things you have done. So, what I am saying here, if a process is enabled infinitely often, then it will run infinitely often. Okay. So, again there are two propositions, run and enable, and there are infinitely often. So, infinitely often I have already encoded, right. So, basically the process is enabled infinitely often is globally future enable, right, and run infinitely often means globally future run, and this implies this, right. So, GF enable, if process is enabled infinitely often, so GF enable implies it will run, the process will run infinitely often. So, GF run. So, this is how I will encode this property. Okay. So, this is what the encoding for this property. Now, take another practical example from lift. So, you know the lift goes up and down. It's say suppose it's going up, it's now in second floor. Somebody goes into it and put a request to going up to fifth floor, right. So, under this scenario, this statement is valid, right. So, what is saying that upward traveling lift, so it's going up, it is at now in second floor, does not change its direction when a passenger wishes to go to fifth floor. Okay. So, here I have to identify the proposition first. So, first thing is that every floor should have a proposition, second floor, third floor, fourth floor and so on. So, I have fourth floor and fifth floor, so second floor and fourth floor is propositions, and we also proposition for first floor, second floor, third floor and so on, right. One is direction, right. So, direction can be up or down, right. So, I will basically can take two proposition, direction up is true means it is going up, direction down means it is going down. Okay. And there is also a request, because some passenger wishes means some request, right. So, if I try to encode now, so I got the proposition, floor, first floor, second floor, direction, request and so on, right. So, then what I will do, I will write if the, so it is basically in second floor, say second floor, and direction is up, and there is a request, right. If this is happen, implies it will go, the direction will remain up until you reach the fifth floor, right. So, this means this, right. So, if you are in second floor, leave it to second floor. So, remember here the second floor, direction up, request, these are all propositions. So, what I am writing here is the lift is in second floor, the direction is up, it is going up, and there is a request, implies the direction will remain up until you reach the fifth floor, right. So, this is how I should encode, right, and this should happen globally. Okay. So, that globally, if it is in floor 2, if the direction is up and there is a request, implies the direction will remain up until it is the fifth floor. Okay. So, this is the lift controller example. Now, I will take one more example of the printer sharing example. You think about that there is a printer in the network and there are two persons, which is Peter and Betsy. So, they want to use the printer. So, they are working, they can print anything in the printer, and the constant only that at a time printer can only print one of his thing, right. They cannot print together in the printer. So, this is the case. So, in this case we will have proposition like this, and then I will encode certain property, so that it basically ensures that the printer sharing is happening in a proper way, right. To make sure that the printer sharing happening proper way, I have to identify certain properties. But as I mentioned earlier, we have to first identify the propositions. So, for Peter there can be three propositions, right. One is Peter request, that means Peter It indicates that it basically request uses the printer. I want to print something. Peter use, that means it indicates Peter uses the printer. It's actually printer is now printing the document of Peter. And Peter release, it indicates that Peter releases the printer. So his printing job is done and he release, make it the printer available. Okay. So similarly, I will have the same three requests for Betsy as well. So that Betsy does request, Betsy dot request. Similarly, Betsy dot use and Betsy dot release. Right. So we will have 6 propositions. Now let us see the LTL properties. So first one is the mutual exclusion. It means only at a time one user can use the printer. So I have to encode that using those 6 propositions. Next one is finite time of usage. What does it mean? User cannot print only, can only print for a finite amount of time. That means you just keep printing and the other person, printer is keep printing infinitely and the other person never gets a chance. That is cannot happen. So if you start printing within, say you have 5 pages, 10 pages, 30 pages, within finite of time, in finite of time, you will complete your printing, right? So finite time usage. And then no starvation. That means if you want to print something, eventually you will get time, you will get access to print your document, right? If a user wants to print something, he will eventually able to do so. And absence of blocking, that means user can always request to use the printer. Okay. And alternating access, I am just saying ki it is strictly alternate. So if Peter prints, until Betsy prints something, you will not get chance, Peter does not get chance to print, right? He has to wait until Betsy prints his document. Okay. So let us say I have to encode these 5 properties. So we will do quickly. So mutual exclusion is easy. So that means this Peter dot use and Betsy dot use, this cannot happen together, right? Globally, Peter dot use and Betsy dot use cannot happen globally, right? So if you convert, it is basically it is written here. So this is globally Peter use and Betsy use cannot happen together. So if I just rewrite this, this is also can be written like this: globally not of Peter use or not of Betsy use. You can write this way also. So where I just put this negation inside and use this De Morgan's law, right? So it's basically saying that at least one of them should be 0, right, to make this happen. The next one was the finite time usage, where I say ki if a user can print only for a finite amount of time. It means what? If Peter try to use, so Peter use means it is Hughes using, implies in future Peter will release it, right? And this is globally true. It means if Peter is using, in future definitely he has to release. It is not Peter use, it is globally Peter use true, right? So if you write globally Peter use true means it is always printing, Peter is always printing. So that is not the case. If he gets access, that means Peter is using this, in future he will release it. And same thing for Betsy as well. Now individual starvation, what I am saying that if wants to print something, so that means if Peter requested, right, Peter requested implies in future Peter will get the access, right, Peter dot use, and this is globally true, right? This is what I have written here, that if Peter requested something, he eventually able to use it, and similarly for Betsy. Then the last 4th one is absence of blocking. That means user can always request the printer. That means infinitely often he will request, right? So that means GA Peter request and GA Betsy request. Okay. So can always request means anytime in future he will get another request from Peter or Betsy, right? So it is basically infinitely often. Okay. So GF Peter request and GF Betsy request. The alternating access is interesting. So what I am saying that if say Peter is using, that means what happened in next state, Peter not use will be true, right? So, until Betsy use, I would say here it should be Peter release. That means Peter release means Peter has already printed now. It means it will not use until Betsy use. Okay. So it basically saying that if Peter release the printer, that means his printing is over. Now he has to wait until Betsy use it, right? Same thing if Betsy release it, that means he's completed her printing. In the next state, she has to wait, not Betsy, until Peter use. Okay, so this is basically on alternate way, right? So if Peter releases means Betsy will use, then only Peter can use, and if Betsy release it, that means Betsy has uses now. Now Peter will get the chance to print it, and then only Betsy will get again, right? So this is a little bit tricky, but this actually takes your alternate access pattern. Okay. So in general, in LTL, the property, we can take any property which basically encodes certain things on context of time, but we can categorize this property in three different categories, right? One is safety, one is liveness, and one is fairness. Okay. So I'll just take the same example of the printer and try to see what property was kind of safety property, what property was liveness property, and which one is fairness property. Okay. So the safety properties, what it says, it basically says that something bad never happened. So that means we are in always safe state, right? Like that, you can think about that. I'll never reach to the deadlock situation, right? So that means deadlock is a bad thing, and deadlock never happened in my system, right? So that means I am always safe, right? Similarly, in my example of this printer, what I am saying that printer never, both of them can not use at the same time, right? So that is basically kind of a safety property, printer safety, that if both of them get access, that is not a acceptable scenarios, right? So it's basically printer is always in safe scenarios. That means only one is actually get chance to print. Okay. So in general, the safety means something bad never happens. We are always in safe state. Next one is liveness. It basically says that liveness means something good eventually happen, right? Something good eventually happen. So for my example of this printer, so that means if you are requesting, you will get to use, right? So basically when you print, you request for the printer, eventually get access. So you good happens for you, right? So the printing is, you are want to print and you get chance to print, right? So so this kind of properties are basically liveness property, and it says that something good eventually happen. And fairness is that you can understand something is fair means you are not ignoring somebody all the time, right, or infinitely. So in a scheduling context, or in our example, in the printer example, what we have written that if you request infinitely often, you get chance to use this, right? So this the example of if you want to request, you will get use eventually, right? So that means it is not something that somebody is having a starvation. You are not waiting indefinitely to get your access, right? So that is fairness. So in general, we can actually take property and think about whether it's a fairness property, whether it's a liveness property or a safety property. And usually during verification, we have different complexity of checking these properties, right? So which we will discuss more in detail when we discuss the LTL algorithm. So I will strongly suggest you take more examples and try to encode this LTL property on your own, and that will help you to understand the more about this LTL and how to encode and so that you will be get ready to take any practical designs and can identify the property to be verified there. Okay. So thank you.